Okay, we're going to continue on here. We're talking about transition metals, and really last time we got into the main part of the chapter, which is coordination compounds. And a coordination compound basically contains two things. It has a counter ion, and it also has a complex ion. Remember, a complex ion is really a compound that has a metal in the middle, a lot of times a transition metal that has a charge, a positive charge, and a bunch of ligands that are attached to it, which are Lewis bases. And when we talk about a sort of a coordination compound, it is much like an ionic compound. It is usually a neutral type of situation. There's usually a positive guy and a negative guy, really your cation and your anion. And you can have a counter ion that's positive, and that would mean that your complex ion is negative. You could also have really the reverse situation where your complex ion is positive, and then you would have a counter ion that is negative. So again, usually you want to kind of balance out the charge to zero, like in an ionic compound in general. And it's really important, as we'll talk about here in a second, sort of the charge on your complex ion. So it may either require you to, for example, name it a certain way if it's negative versus a different way if it is positive, the complex ion. We obviously talked about oxidation numbers, and typically speaking, again, complex ions are usually in these brackets. And again, the counter ion can either be on the left-hand side, which means you would have like a positive counter ion. Or you can have obviously the opposite there, where you have your complex ion that comes first and your counter ion there on the back end of it. We oftentimes can look at the oxidation numbers of the metal in the complex ion, and also something known as the coordination number, and that is the number of atoms directly attached to the metal. And remember that there are certain ligands which are Lewis bases, like water, ammonia, chloride. These are what are referred to as being monodentate, which means they can bind basically one place per molecule. There are also some that we talked about. En is an example, oxalate, even carbonate. These are bidentate, which means for every one of those, you can basically get two. So if you took the En, which is this guy here, when this guy goes and binds to the metal ion, it's going to bind in both nitrogens to it. And you get basically a 2-for-1 in terms of the coordination number. There's also ones that combine in a lot of places, like EDTA could do 6, as we talked about. This is sometimes referred to as being polydentate as well. So a reminder that when you do see the formula, again, sometimes people think when they kind of see the number underneath in terms of the ligands that are present, that's always going to be the coordination number. And it will be if it's monodentate, but if you have some bidentate or polydentate type of ligands involved, that will change the coordination number. All right, so we talked about last time the oxidation state and all that. Let's now talk about how we go about naming these coordination compounds. And to name these coordination compounds, a few interesting things that sort of happen. Some things are kind of like normal. One thing that is like normal is, as we talked about, the cations always comes before the anions. So again, it's always positive, then negative, and that goes both for when you write a formula and also when you name something. So you should always do the positive guy first and the negative guy second. Within the complex ion, the ligands are named in alphabetical order first, and the metal comes at the last part of the complex ion name. And that's an important thing to remember. The metal should come at the end of the complex ion part of the name. And what that means is it may not be the actual end of the name. but there is a complex ion part to these compounds and a counter ion part. So if you have a positive complex ion, then the metal part of that name will come at the end of that part of the naming, and you'll still have some more name on the other part of it, which is the counter ion. If you have a negative complex ion, then the metal's name will come at the end of the whole name, and we'll talk about that in a second. By the way, we do ligands in alphabetical order, regardless of prefixes. So if you had something like aquo or aqua, and you had a chloral, we would compare the C to the A and not the prefix. And sometimes we do use prefixes when we do have more than one of the same ligand within the compound. Speaking of those ligands, a lot of them will end with the letter O. Some will be called by its normal name. There are some exceptions. Water's aquo. Some people use aqua as well. CO is carbonyl, amine for ammonia. As I just mentioned, if there is more than one ligand within the complex ion, we do use prefixes to indicate how many. Di for 2, tri for 3, tetra for 4, penta for 5, hexa for 6. Now, another interesting kind of weird thing that happens with these is if the actual ligand itself has a prefix in the name, we actually would not use those prefixes if we had more than one. We would actually come down to these prefixes here, and that's bis, which means 2, tris, which means 3, and tetrachis, which means 4. So an example of that is that EN that we use. That EN is ethyl endyl diamine is part of the name there, ethyl endyl. I'll just write the last part of it here, diamine. And since the name of this ligand itself has the di prefix in it, if we had something like 2 of these ethyl endyl diamines, we would actually use bis instead of di. So we would use bis in this case instead of ethyl endyl diamine because it already has a prefix. So that is sometimes happens. Also, sometimes people will use it with bidentates like oxalate as well. Sometimes people will use it with that one as well. These kind of bis, tris, and tetrachis. The oxidation number of the metal, which is part of the complex ion, is written in Roman numerals following the name of the metal. Now, this is also something that's a little bit different in some cases. And what I mean by that is we do use Roman numerals in most cases. And that's because they are transition metals. We even use Roman numerals on transition metals that we don't usually use Roman numerals on. So for example, if you had silver, which has a positive 1 charge, you would still use the Roman numeral 1. So zinc, cadmium, silver, even though they kind of have fixed charges in this type of naming, we still tend to use the Roman numeral when we name it. Also, as weird as it may sound, you can end up with a neutral metal in the complex ion. And in that case, we sometimes will just use not really Roman numeral, but you put 0 there as well if it happens to be neutral. Now, the main sort of difference is if the complex ion part is positive and you have a positive complex ion, then you would use for the metal the regular name. So iron would be iron, chromium would be chromium, copper would be copper, whatever it may be. If you have a complex ion that is negatively charged, then it actually will not use the regular name of the metal. You will roll with kind of the old school name and will end ate at the end of it. So iron would be ferrate, copper would be cuprate, plumate for lead, zincate for zinc, and so forth. So we kind of use the older school name if you have something that is negatively charged for the complex ion. Here's some examples of some of these ligands. So aqua for water, amine, methylamine here. For our halogens, we kind of roll, it's how we do with organics. So fluorine is fluoral, chloral, bromo, iodo, hydroxo, cyano there for cyanide. And this is what I was talking about in terms of our metals. So once again here, if we have a negative complex ion, so if the complex ion part of your coordination guy is negative, then you should roll with this type of naming. If your complex ion is positive, then you should roll with just a regular sort of naming. Here's a few more of those names. Here you got carbonate, which is carbonato, a little oxalato, like you're ordering coffee or something here, a little carbonel. This is ethylenediamine, which is here. Again, remember that that guy, EN, is used both in formulas and also in names as well. This is actually EDTA down here, this guy as well. So let's take a look at those two that we ended up on, I think, last time, which are these. So remember, if we look at these here, we know a couple of things like we figured out previously when we ended. We figured out that the oxidation state here on the gold is +3, and that's because OH is -1, gives you a -4. There's a +1 out here, gives us a +3 for the gold. We know that this is our counter ion, and this is our complex ion. And by the way, I know just from this arrangement that the counter ion is positive and the complex ion is negative because it comes second in the formula. So the way that we name pretty much counter ions is we just name it like normal. So we just kind of, if it is a positive counter ion, you're probably just going to use the metal's name. That's most likely what you're going to have there. So this would be just potassium. And again, that's for our counter ion in this case. We have 4 of the hydroxides. So again, 4 of the hydroxides is right here is hydroxo, and 4 prefix is tetra. So this is going to be tetrahydroxo. So we got tetrahydroxo. Now, because we know that the complex ion part here is negative charge, and it is -1 charge, which is why we have just 1 potassium here to bounce it out. When we go to name gold, we will have to use not gold, but we will have to use the old school sort of name for gold, which is RU8 here. So we will want to use this again because our complex ion part is negative. So that would be RU8. And we do need a Roman numeral here. So that would be RU8 Roman numeral 3 in this case. So this guy here would be potassium tetrahydroxo RU8 3 in this case. If we look at the other example here that we did at the end last time, and we'll just kind of go through this guy here. We have this. And once again, from the placement here, this is our complex ion, and this is our counter ion. So we do know that this is positive and this is negative. So that means when we get to our metal, we can just use the regular name chromium here. We don't have to use the kind of old school name of chromate. Here again, the chromium had 0 for the ammonia, -1, and there's 3 of them, -3. So the chromium again here had a +3 charge. So we do have 6 of our ligands. So 6 is hexa. And amine is the ligand name for ammonia. Here, because it's a positive complex ion, we will use chromium Roman numeral 3. Now, in this case, it really doesn't matter in either case in terms of the counter ion, how many you have. You basically just kind of use the proper name of one of them. So even though there's 3 of those, we will go with nitrate here. I'll go underneath since I'm running out of room there. So this would be hexamine chromium 3 nitrate. Would be here. And again, a reminder, the reason why we have 3 of the nitrates is our complex ion has a +3 charge. So we need 3 of those counter ions to balance out the charge in this particular case. First off, any question on those names there? Now, if we were just looking at the complex ion by itself, and we wanted to give the name here of just the complex ion by itself, frankly, we just get rid of the counter ion part of the name, and this would be tetrahydroxo arurate 3 ion. So you just got to put ion at the end of it, get rid of the counter ion's name in the name. Same thing over here. If we were just naming the complex ion part, it basically would be through here and just put ion at the end of it. And that would basically be just the name of the complex ion. Now, what I was talking about earlier in terms of the metal comes at the end of the complex ion part of the name, this is the metal, and it's at the end of the complex ion part of the name, as this is the complex ion part of the name. Over here, though, I'll get rid of that. This is the metal's name, and it comes at the end of the complex ion name, but it is not the end of the actual overall name. So it does depend on what you're looking at. Any questions on those there? All right. So if we take a look at this one here, this again is potassium. And here is our counter ion. And this, I'm sorry, that's my complex ion. Complex ion, that's my counter ion there. And if we look at it, let's talk about sort of the oxidation state here of the chromium. That is oxalate, which is a -2. There are 3 of them, which gives us a -6 overall. We have +1 for the potassium. There's 3 of them, gives us a +3. So the chromium here is going to be +3. The coordination number in this case is 6. And again, that is because oxalate is a bidentate ligand, which means for every one of those oxalates, they're going to bind to the chromium in 2 places through the single bonded oxygen in each of those cases. So again, because this is oxalate, I'll draw the electrons there, but basically it will attach to the metal in 2 places per molecule. And since we have 3 of them, that's going to give us a coordination number of 6 in this case. So to name this, we will roll with the whole name here of our metal. Our complex ion is actually negative. Our counter ion is positive. So we do have 3 of the oxalate. And again, if we go to oxalate here, that is oxalato. And 3 is trioxalato. And here, because it is a negative, we will have to use chromate instead of chromium. And we will use Roman numeral 3 in this case. I will say that because this is oxalate and it does have it is bidentate, some people will call this potassium tris instead of tri because of it being sort of a bidentate. Oxalato chromate 3. Any questions on that then there? All right, so why don't you try some here? Here's a few more of the metal names, old school name, regular school name there. So for the top one, we were looking for the name. Bottom one, we're looking for the formula. So see what you come up with. Okay, so let's take a look. Let's take a look at the first one here. Here we have a complex ion part. Here's our counter ion. Obviously, complex ion coming first going to be positive, going to be negative. So we can't just roll with our regular chromium for our metal name. In terms of oxidation state, water is 0. Cl is -1. There's 2 of them, which is the -2. The outside counter ion is also -1. That means here we have a +3 for our chromium to get us to 0. Our coordination number, by the way, here is also 6. 2 chlorides attached and 4 waters attached are all monodentate. That means here we do have 4 waters, so just building our name here, 4 is tetra, and this is aqua or aqua, depending on which way you want to go. We have 2 chlorines, so that's a dichloral situation. And obviously here we have a chromium, Roman numeral 3. So we're going to go alphabetical again, ignoring the prefixes. So looking at A versus C in this case. So that's going to give us a tetra, aqua, dichloral, chromium, Roman numeral 3. Now our counterion is chloride, and it doesn't matter how many we have, we just basically call it chloride here, and that would give us our name. Questions on that one there. Now we want to write the formula here for this guy. So this is our complex ion part. I know that for a couple of reasons. I see cobalt is regular name, so that's positive complex ion. I also see the metal name at the end of it. This sulfates are counter ion in this case here to balance out the charge. So tris ethyl endyl diamine, again, because this has a di in its name, that is why they use tris here and not tri. But that basically means we have 3 of these guys, and we have a cobalt with a +2 charge there. And that's our complex ion part. So we could build that. Our complex ion would be cobalt. We have an En here with a 3. We do want to kind of figure out the charge here. So this guy is 0, and the cobalt is +3, which means the complex ion part actually has a +3 charge. And I'm sorry, that's actually +2. Bad there. +2 charge. So the complex ion actually has a +2 charge. And that's important when we look at our counter ion, which is sulfate. Sulfate has a -2 charge and a +2 charge. That means we really just need one counter ion here to balance it out. And that will give us our coordination compound, which looks something like this, basically. Any questions on that guy there? All right, let's try a few more here, just to get the hang of it. So I want to go names. Okay, so let's take a look here again. Just by the positioning here, our complex ion comes first, which means it's positive, and that obviously is our counter ion, which would be negative. So figuring out our oxidation state here, we got 0 for the ammonia, we got -1 for the chloride. We have on our counter ion -1, and there's 2 of them, gives us a -2, -3. Again, here cobalt's going to be +3. We do have a coordination number here of 6. There are 5 ammonias attached and 1 chloride attached directly to the cobalt in the complex ion. So we have 5 ammonias. So that is penta for the prefix for 5, amine for the name for ammonia. We have only 1 chlorine, which is a chloral. We actually do not use mono in the naming of these guys, so we don't typically use mono here, so we just call it chloral. And again, because the complex ion is positive, we could just use cobalt, the regular name of it. So again, alphabetically here, we're going to go with A versus C, and that's going to give us pentamine, chloral, cobalt 3. And here again, no matter how many we have, we just basically name one of them. And the counter ion here would be chloride in this case. Any questions on the name there? Coming here, that is my complex ion here, which comes second in the name, which tells me it's negative. Here's my counter, which is going to be positive. Looking at the oxidation state here, we got +1 for our potassium. That's a +3 total. Over here, that's cyanide, which is -1, so that's a -6 total. So here it's going to be +3 again. Not all metals will be +3s, but they happen to be in these examples. Because our complex ion is negative, we will not use iron here, but we will use ferrate, the kind of older school name. We will start with our counter ion, and it doesn't matter how many we have, so that's going to be potassium. Hexacyano, which is cyanide's abbreviation there as a ligand. And this will then be ferrate, Roman numeral 3 in this case. Questions on that name or those names there? All right, so let's take a look at two more here. We're going to go formulas on these guys. So write the formula, see what you come up with. Okay, so let's take a look. So really with these, when you have the name, you just kind of want to build the parts of it. Once again, this is the complex ion part here as we see the metal at the end of that part of the name. And again, that's what I was talking about before, not the end of the name, but the end of the complex ion part name. This would be our counter ion here. The chloride now would be our complex ion. So triamine is basically 3 ammonias. Bromol is a Br minus, and platinum with a Roman numeral 2 means it has a +2 charge. So we have basically everything we need here to build our complex ion. We'll go PT, a little NH3, 3, and a Br. Now, the important thing here is to figure out what is the overall charge happening here with this complex ion. We know this is +2, this is 0, and that's -1. That means that my complex ion here really has a +1 overall charge. That's important to tell us how many of these counter ions, which in this case is chloride, we would need. And in this case, we'd actually just need 1 to balance it out. And that would get us our coordination compound basically just by putting our chlorine in there, and we would have it. Any questions on that one there? Coming out the second one, that's potassium. That is my counter ion because the transition metal there is not at the end with the Roman numeral. This part here is my complex ion. So I know potassium's K plus is my counter ion. Hexafluoral means I got basically 6 fluorines. And cobaltate 3 means I have a cobalt with a +3 charge. That means if I build out my sort of complex ion part, I'll look something like this. This being +3, this being -1, and there's 6 of them. So overall here, I'm actually rolling with a -3 charge for my complex ion. And again, that's important because in this case, we actually need not 1, not 2, but we actually need 3 of the counter ions here to balance out the charge. So that would give us K3COF6 as our proper formula. Any questions on naming or writing formulas for complex ions or coordination compounds? In this case here, the coordination number is 4. Here, the coordination number is 6 in this case. So again. All right, so then let's talk a little bit about some other aspects of complex ions, and these are isomers. And isomers are essentially has sort of the same formula, if you will, but it does have some different properties, and sometimes that's different connectivities. There's a few different types of isomers. There's structural isomers, which can be coordination or linkage isomers. We're going to talk about each of these in a second. Stereoisomers have the same bond, but different spatial arrangements of these bonds. That could give rise to a cis or a trans isomer or an optical isomer. So let's take a look at a couple of these here. First off, a coordination isomer is one such as this. If you kind of look at both of these formulas, they have the exact same thing. So we have 1 chromium, 5 NH3s, 1 sulfate, 1 bromine, 1 bromine. So they have exactly, basically the same things in it. The difference, though, is in the top one here, this is our complex ion. And this is the counter ion. Now, in the top one, the sulfate here is actually a ligand. The sulfate is actually attached to the chromium, in this case, part of the complex ion. The Br here, or the bromide, is just there to balance out the overall charge. Now, on the bottom one, this is our complex ion, and in this case, the sulfate is our counter ion. And the difference here is the bromine is actually a ligand and directly attached to the chromium. So although they have the exact same stuff in each of them, in one case we have a sulfate acting as a ligand, and the other case we have the bromine or bromide acting as a ligand. And again, that is what is known as a coordination isomer. Another type of structure isomer is what is referred to as a linkage isomer. And in a linkage isomer, what you have is the exact same ligand attached, but the ligand itself can actually attach in one of two elements, if you will. So if we take NO2, we basically have an N and an O and an O. In certain cases, the ligand will attach using the nitrogen, and that is what we see right here. And in other cases, the ligand will attach through the oxygen in this case. It is the exact same ligand in each case, but the linkage to the transition metal, or the cobalt in this example, is different. So thiocyanate, for example, SCN minus, I could also do that. I could go through the nitrogen or the sulfur, and again, depending on sort of what it wants to out of carbon in that case, depending on where it wants to attach, it can give you a different isomers, different properties. So a linkage isomer is one where we use a different element on the same ligand to make the attachment. You can see in each of these cases, it is still monodentate in terms of how it's attaching. It's just attaching in one place. Just in one case, it's the nitrogen attaching. In the other case, it's the oxygen. Now, stereoisomers are geometric isomers, are cis or trans isomers. They have the same atoms and the same bonds, but they have different bond angles. And they are common in square planar complexes. If you remember square planar, expanded octet, basically makes a plane there where everybody's attached and some non-bonding electrons sort of happening out of the plane. And that's your octahedral sort of arrangement. And cis and trans isomers, cis means basically the same side, and trans means opposite side. And in organic chemistry, you come across a lot of cis and trans. And usually in organic chemistry, you're dealing with a double bond. So if you have a group that's on the same side of the double bond, that's known as cis. If you have a group that's on opposite sides of a double bond, then that is known as trans. Here, though, we don't really have a double bond. So we're talking about really the plane of the molecule. So in this case, basically, this is our square planar. We have the ammonias in the same side of the plane, and that would be cis. You could also look at the chlorides as well. They're on the same side. Here, this is the trans. We have basically the ammonias on opposite sides, and you could also look at the chlorides here that are on opposite sides as well. Because of that, it does get some different properties that occurs. We could also see this in the octahedral arrangement. If you remember octahedral, basically 6 electron pairs. And here, when we talk about it, you can kind of think of this as being the plane of the molecule. And in this particular case, we have a chloride above and below the plane of the molecule. And that is what is referred to as trans, opposite sides. Here we have basically the chlorides on the same side of the plane of the molecule, basically. And that is what is referred to as being cis. So in octahedral, we're kind of on opposite sides of the plane in the middle. And if we're kind of on the same side, it's going to be cis. And we would name these the exact same way. It's just sometimes they'll put cis or trans in front of them. Now, optical isomers have the opposite effect on plane polarized light. And they are sometimes referred to as being chiral. And a chiral molecule basically means that if you take that molecule and you stick it up to a mirror, so if you take this molecule, stick it up to a mirror, and you take out the mirror image, it will not be able to superimpose. So something will always be off. So a very easy example is your hand. If you stick your hand up to a mirror, you get your other hand staring at you. And if you pull out the mirror image, you will not be able to sit these two on each other correctly. although the thumbs are right here, one's palm up, one's palm down, you could rotate it around, then that's not going to work. If you even rotate it this way, they're both palm down, but thumbs are now on the wrong side. So you can never sort of rotate it enough that there's always a bond that's off, and there's always a bond angle that's off. And there's also, that is what is referred to as being chiral. What's referred to as being achiral means that you have a mirror image that you could actually take out and you could rotate it and it will fit perfectly on it, and fit perfect. You could actually measure the angle of reflection there. So for example, if we look at this here, isomer 1 and isomer 2 in this case are mirror images that cannot be superimposed. And again, if this was our original sort of isomer here, when we sort of reflect this guy off into the mirror here, what ends up happening is we actually create a different bond with that reflection that occurs. And that happens, let's get rid of all that there. If we look right about here, in the original isomer, these two guys are bonded together. But when we do the reflection, what ends up happening is we create this bond where it's now bonded to the guy in the back, which is the reflection that occurs. And because of that, if you try to take these two guys, or this guy here, which is the mirror image, and you try to rotate it, because it has these really different bonds that occurred, it will never sit right on top of each other. So it'll be a chiral molecule. It will not superimpose correctly on the mirror. Here again, we see our trans where the mirror images are identical. So in this particular case, when we sort of go into our mirror, we actually end up with the exact same connection that's happening here between these guys. We got the exact same sort of connection. Again, if we look at our cis over here, we're going to run into that same problem where we kind of make in our mirror image this opposite connection here that's not going to pass. So a lot of times cis is the ones that kind of do that. They kind of make these chiral guys that will not superimpose on each other, because as it gets reflected in the mirror, it makes this opposite sort of connection that you don't have in the original one. A lot of times though in our trans, you kind of get it to reflect okay. Now, enantiomers are two molecules that have mirror images of each other that are non-superimposable. And sometimes these are used in drugs, and sometimes one molecule, because of the bond, will be effective, and the other one will not be so effective in terms of its bonding. The last thing we're going to talk about here in terms of this chapter is bonding that occurs in complex ions. And it does involve a couple of things that maybe from the past, hybrid orbitals. And if you remember hybrid orbitals, we have things like sp, sp2, sp3, sp3d, sp3d2. These are related to electron pairs, right? 2 electron pairs, 3 letters, 3 electron pairs, 4 electron pairs, 5 electron pairs, and 6 electron pairs, basically. Remember as well, when you're doing that, you count single bonds, double bonds. Everybody counts as 1 electron pair. Now, the Vesper model does not work well for complex ions. So really, when we think about complex ions, we oftentimes think of it more as a acid-base reaction, and more specifically, a Lewis acid-base reaction. And where we have our metal, that's our Lewis acid, is deficient in electrons, and our Lewis base is our ligands that are coming in to bond to it. The hybrid orbitals used by metals depends on the number of ligands present. So here we can see basically 6 ligands, and 6 is going to give us our sp3 d2. And that basically is your octahedral arrangement that occurs. These are very common arrangements for complex ions. We have tetrahedral, which is 4 electron pairs. We have sort of the expanded octet square planar. And really, these two guys usually roll with a coordination number of 4. They also have linear, which is sp. That usually is a coordination number of 2. It's usually associated with that sort of geometry that occurs. And here's what that table sort of shows you. So these are the common ones. Coordination number 2, linear. 4 and 6, tetrahedral, square planar. Our octahedral, again, kind of our sp, our sp3, sp3d2, and our sp3d2 happening there. Now, when we talk about transition metals, which are typically the metals that are involved in the complex ion, they are d orbitals we are talking about, and remember transition metals start at the 3d sort of section. And there are 5 different d orbitals, basically, and these are the 5 different d orbitals. And when you have, for example, if we looked at the 3d orbitals, which is our 3d subshell, if we had no ligands present, all 5 of those individual d orbitals would be the same energy. Basically, they would all be in the same energy. And that's important, as you hopefully remember how electrons go into an atom is they will fill up lower energy first and then start filling up higher energy, right? They also fill electrons one at a time before they start pairing off. That's what's known as Hund's rule. Now, what happens when we actually start to add ligands to the mix is we actually will get a separation of the 5 individual d orbitals in terms of their energy. And what we're looking at here is actually for a coordination number of 6 and an octahedral geometry. And what ends up happening is we actually get a lower pair of d orbitals in terms of energy, and we get these guys that are the squared ones in a higher energy level. And the difference in the energy between the lower d orbitals and the higher d orbitals, that is what is referred to as crystal field splitting. And crystal field splitting is sometimes abbreviated with a delta. Sometimes you may even see it as just a regular energy sort of abbreviation. Now, what is the effect of this? The effect of this is how the d electrons will basically be distributed. And we're talking about the d electrons from the metal that's in the transition metal. So, for example, if we have a relatively small crystal field splitting, what's going to happen is as the electrons go into these orbitals, they will go in one at a time and decide, well, that's not too big of an energy difference. So they will just start filling like normal one at a time, and they'll come back if necessary and start filling. Now, if you have a larger crystal field splitting that's occurring here, what's going to happen is these electrons, as they sort of get distributed, will get to the end here and decide that is too much energy to go up there. So we much rather fill up what's on the bottom first, the lower energy, before we're sort of forced to go to the top. And that's going to give you a difference in, for example, how many paired electrons you're going to have and how many unpaired electrons you're going to have. The more unpaired electrons, that is what is known as being paramagnetic. Dimagnetics, when the electrons pair off, right? Electrons have spin and opposite spins are paired with each other. And we could actually calculate the crystal field splitting by using an equation you might be familiar with, and that is your basically E is equal to H times the frequency. H is our Planck's constant. That is our 6.63, bless you, times 10 to minus 34 joules times seconds. That is our frequency, which is usually in reciprocal seconds or hertz. Now, you may also remember another equation that goes with that. C is equal to the wavelength times the frequency. That is the speed of light, which is 3 times 10 to the 8 meters per second, or 2.997, if you like that number better. That is our wavelength in meters. and that is our frequency in reciprocal seconds. Now, if you solve for the frequency here, is c divided by the wavelength, which means E is equal to hc over the wavelength. You can substitute that into that equation. And what that allows you to do, as we talked about, is essentially if you know the wavelength or the frequency, you can basically figure out the energy difference between the lower d orbitals and the higher d orbitals. And clearly, as we know, when we do any type of absorbance, we take the maximum wavelength, right, is what we're shooting for. And that's what we want to set everything to. And speaking of that, as you also are familiar with, hopefully, right, the color, for example, of the solution that we see is complementary to the wavelength of light that's being absorbed, right? So if we see a red solution, we actually wouldn't set, for example, the wavelength to red's color, our wavelength, we'd actually set it to its complementary color, maybe more of a greenish type of color. So with that being said, just to look at this problem, which I think is filled out for you on your paper. So let's talk about how we would get there. If we have this complex ion and it has a maximum absorbance of 470 nanometers, what color is the complex and what is the crystal field splitting? So the color of the complex is, since we have 470, which would be in this region, it's absorbing at 470. So the color would be the complementary color to what we see. And that would mean that the solution would appear orange to us. That again is why earlier on in the semester where we did the iron and the thiocyanate, it was a red solution, and you picked a wavelength on this side over here, closer to kind of the green or bluish area, which is the complementary color. Now, with that being said, we can convert this. Remember that it does need to be in meters. So 1 nanometer is 10 to the minus 9 meters. So this is our h, this is our speed of light, and this is our wavelength that has been converted to meters using our nano conversion. And that gives us a crystal field splitting of 4.23 times 10 to the minus 19 joules. This is actually per atom. And if I want it per mole, I could then use Avogadro's number here to convert atoms into moles. And that would give us, in this particular case, a crystal field splitting of 255 kilojoules per mole. So it's a very similar calculation you probably did in Chem 50 to figure out the energy or the wavelength here. Any questions on that there? So how do we know if we're going to kind of get a big splitting that's going to occur or a smaller sort of splitting that's going to occur? And it has to do really with the ligands that are present. There are certain ligands on this side, which are referred to as weak field. And weak field ligands will give you a smaller separation of those orbitals. And on this end, it's a strong field, which again will give you a much larger separation of the lower and higher sort of orbitals. And again, what this affects is if I had 4 electrons, d electrons I want to distribute. In this case, we go 1, 2, 3, and I go, that's not too bad. We'll kind of do that. Here again, it would go 1, 2, 3, and decide that's too high. I'd rather go here. What that's going to give us, for example, here on the left is 4 unpaired electrons. On the right, we actually have only 2 unpaired electrons. And this sort of situation is what is referred to as a high spin complex. A high spin complex is something that has a lot more unpaired electrons than paired electrons. This would be what is sometimes referred to as a low spin complex. It has a lot more paired off electrons than unpaired electrons. And that's a very common sort of question that you're asked is, what type of complex is it, or how many unpaired electrons are there? Now, the ones in the middle can depend. Sometimes you would be asked, for example, to draw the one that is the high spin complex, or sometimes you may be asked to draw the one that's the low spin, or weak filled, or strong filled. And in some cases, it may not even matter, whatever it is. And if you're not given any information, it may not matter. So for example, if you had somebody that only had 3D electrons, that means that no matter what you do, nobody is going anywhere but the bottom row, basically, in this case. So if you just had 3, you wouldn't need to even worry about the top ones. So it won't make a difference, kind of what you do it for or not. So for example, if we look at one here, like our nickel Br6, in this case, we have -1 for our bromine, -6. That means our nickel here has a +4. Nickel on the periodic table there is 28. So if we write the electron configuration, that is argon 4s2 3d8. Nickel with a +4 charge would have 24 electrons. Remember, as we talked about earlier, transition metals will lose the S's first and then come into here, which means we will end up with argon 3d6. Those 6 electrons that come from the nickel is what we would distribute into our crystal field splitting. So in this particular case, the coordination number here is 6, which means we would get the octahedral splitting that we've been looking at. That is so badly spelled, octahedral. There we go. And that's going to give us our lower d orbitals, our 3, and our higher kind of 2d orbitals. Now, what determines if this crystal field splitting here is going to be large or small is the ligand that's present. And if we come over here, we see Br is over here on the weak field, which means that this is going to be small crystal field splitting. This is going to be a weak field. And that means that when we go to distribute our 6 electrons, we would go like this, 1, 2, 3, and then we'll decide that's not too bad, 4, 5, and come back and distribute here our 6th electron. And that would give us 4 unpaired electrons. Any questions on that there? Now, if we take a look at the guy underneath it, just as comparisons, we have our NiEN3 +4 in this particular case. And this nickel is also going to be +4, as that is 0. And we will again have our 6 nickel guys that we need to distribute. So the coordination number here is 6. Again, because this is bidentate, so 3 times 2 is 6. So it is also going to do our octahedral splitting. But when we look at En, it is closer to a strong field ligand. And because of that, this is going to be kind of large, strong field. And what's going to happen in this case, as we distribute our 6 electrons, 1, 2, 3, it's going to decide, no, thank you, I don't want to go up there. 4, 5, and 6 in this case. And we will have 0 unpaired electrons. Even though they both have nickel with a +4 charge, because of the ligands that are present, we actually get different compounds. This would be more of a high spin complex. This obviously has a lot more paired electrons, which means it would be a low spin complex in this case. Any questions on that there? All right, we're going to lay it up there, I think, for